Thank you very much for the opportunity to talk to you. I hope that you can hear me. And there's an alternative title, which could be the combinatorics of the sequence A2212 in the Encyclopedia of Integer Sequences. And this sequence starts with 1, 1, 3, 10, 36, and so on. I often go to the Encyclopedia of Integer Sequences and I get a lot of inspiration. It's really a treasure trove. And now let's start with the Skew Dyke pass. So Dyke pass, I think everybody knows, with up steps and down steps and coming back to the x-axis and never go to negative territory. And there is a variation, I think, introduced by Emmerich Deutsch, which allows a third type of step, namely a left step. But of course, one should never go up and immediately do a left step after that. So these things should not cross each other, or so no anomalies should happen. So I have in this picture all 10 skew Dyke paths of length 6, so meaning 6 steps. So we see the ordinary Dyke paths, and then we see some more exotic looking ones where you have these left steps or southwest steps, if you wish. Here is one, and here is one, and so on. So we have 10, and maybe you remember the number 10. I remember I saw a talk by Don Knuth. It's the 2014 Christmas lecture. And he always said, oh, the number 55, and one should look out for the number 55. And he always said speed limit. So here I just say, look out for the number 10, because I will use it as a running example. Now, what I prefer instead of doing these left steps is to draw, instead of this southwest steps, a southeast step. But to make sure what it is, I prefer the red color. So now we have things that look like Dyke paths, but occasionally red down steps. And so what are the syntactic rules that we have to observe? That an up step cannot follow by a red down step, because that would be up and going back, and this we don't want. And similarly, if we go left and then immediately up, so this is also forbidden. But otherwise, I think this notation is a little bit more intuitive. So what happens here, I think, is best described by this type of graph, where one can do up steps in the, as you can see in the first layer of these graphs. So you can do an up step, another up step, and so on. And then after the up step, you cannot do a red down step, but you can do a black down step. So that's what you have to do. And then you can decide whether you continue with red down steps or black down steps or any mixture of them. But to come back to the layer where you have up steps, so you cannot go from here directly to the up steps. So you have to first do a black down step, and then you can continue. So I think everything that one wants to know is just described in this picture. And if one wants to do enumeration, then one should first consider that we are interested mainly in what happens when we come back to the level 0. That means to the x-axis. But we are also interested in the other guys, namely when we come back to a level j, let's say. So this, and this. And we use the following generating functions. Since we have these 3 layers of states, I call them F, G, and H, and they have indices. And we just consider, let's say we have ji, and z marks steps, and I just consider what could the last step be that brings me to ji. And so you could either come from here, this is ji plus 1, or you could come from here, which is fi plus 1, and or you could come from here, which is hi plus 1. And we do this for all these three sequences and write down the recursions. And so all these functions depend on z, which I don't make explicit, not to overload the description. Okay, so what one does now is one introduces a second variable called u that takes care of the letter I. So I is always the current level of this skew dark path once you scan it from left to right. And then one translates all these recursions. So you think that everything is multiplied by u to the I and summed over I. And once one has this one, and you ask Maple to solve the system, then we get these three expressions for F, G, and H. Now, a naive thing would be, so you have this special appearance of G of naught, H of naught. So naively you would think maybe I can now plug in u equal to 0 and solve the system, but that doesn't work as it gives you just void equations. So we are in the realm of the kernel method. And as we notice, we have in the denominator in u quadratic polynomials, and they can be factored as follows, u minus r1 and u minus r2 and z, and these two solutions are depicted here. And as it happens, one of these factors is bad and has to disappear, otherwise we would not get a solution in power series. So fortunately, so first of all, the bad factor is u minus r2, but at the moment you don't really need to know what r2 is, and fortunately you can ask a computer to divide this factor out in numerator and denominator everywhere. And once you have done this and you write some nice abbreviation for this root, then one has explicit expressions for all these three functions. From now on, we only want to the sum of the three. I mean, one could work out all of them separately, but that's not what I'm doing now. And so we sum up all these three things. And as you see, the variable u only appears in this place. And if one looks at the coefficient of u to the j, that means we end on level j. So altogether, the coefficient of u to the j, z to the n, counts the partial path, skew dark path, I mean, ending at level j and having length n. Okay, the special case of interest is, of course, when j is 0, because then we are back at the x-axis. So, and here is the generating function that one obtains here. One sees that only even powers of z can occur. And if you expand this, you get the sequence that we discussed, 1, 1, 3, 10, etc. Okay, so that was the start of this discussion. And if you want something explicit, there is the following approach. If you think about dark paths, you can write them with Catalan numbers. But here you have to do something slightly different. And you could use these coefficients, namely, instead of a binomial, you take 1 plus 3t plus t squared and the powers of this, and think about it expanded. So these I might call weighted trinomial coefficients. And with them, one could write explicit expressions of all these quantities. I don't go further into that. Yeah, and now once we have this basic enumeration, we can think about various other things related to the skew dark path and the kernel method. And so let's discuss one of them. Again, I found a sequence in the Encyclopedia of Integer Sequences, and it has this number 128723, and it's skew dark path with the additional restriction that it's not allowed to have a peak. I think we heard the word peak before, with this Downton Abbey thing that I also saw years ago. So a peak is just up step followed by down step, and it can only be a black down step because the other ones are forbidden anyway. So, but this thing on the ground level are forbidden. So the peak at level 1 would be forbidden. Now, if we look back at the graph that I've shown you before, we can exactly see where we would get such a peak at ground level, namely if we go up and then we would go down immediately. So that is forbidden. Everything else is as before. So either we just erase this arrow, and we said we are not allowed to go here, but we can do a little bit better, and we can say we enumerate all these paths and count how often we run through this magenta type edge. So otherwise one does very similar things and sets up all the recursions. One has to be careful because at the beginning it's slightly different, but all this is doable, and then one can get results and express it with the same type of roots that we have seen before. And then there is another area, namely skew dark paths with catastrophes. Catastrophes in this context were introduced by Banderier and Wallner, and so we have the same basic drawing, but it could be at any step that you fall down to the origin. So I think there are some games for children where this could happen, that wherever you are, it could happen that you have to go back to the start. And so so these are the paths, and it's indicated that there's an additional step that brings you back to the origin. Now, here as well, one can follow the same approach and just do the computations. I'm not going more into that. But now let's go to trees. An old favorite of mine, of course. So let's consider ordered trees, as you see here, or planar tree or whatever. And how does one translate that into dark paths? One just walks around the tree, and one sees every edge exactly twice, the first time and the second time. And then if you walk down, you do an up step, and if you come back, then you do a down step, and so on. And so if the number of edges is n, then the length of this dark path is 2n. So this is a very basic thing, and I'm not telling you anything new about this. And one can do this now for the skew dark paths as well. And you recall that the skew dark paths have some red downwards edges. And in this case, we get some trees that are marked. And so all these things go both ways. Let's look at 10. So 10 is the number of objects here, and I drew all ordered trees, but some of them have now red edges, and they are all different now in our setting of the marked trees. And so there are some that don't have red edges, so they correspond to the ordinary dike paths, but the red ones, so what one does here is one walks around and does the usual thing, but when you come back, then the red edge means a red downstep, and this one also a red downstep. So I think I have some systematic drawing of these 10 examples. So let's look at just one from here, let's say. So you go up and down, that's as usual. Then when you go up, you do nothing special, but when you come back, so here, and then the last one is red. So that's the translation. And if you don't like the red edges, you can still do the left edges. And so look at the 10 examples. Now let's go to equations, symbolic equations, namely for the marked ordered trees. So as we see, the red edges are something special. If you don't think about the red edges, you just have the ordinary equation for ordered trees, which means it's either a node or a node followed by any number of ordered trees. The only thing that one has to be careful about is if the rightmost edge is red. And then the syntactic condition tells you that you cannot stop here immediately, because what would happen then if you translate that into a dike type path, that you go down and you come back immediately with red, and that's exactly what's forbidden. So that's the equation. And once one has a symbolic equation that Philippe Flageolet was very fond of, then you can translate this into a generating function and do this one with A, and this time Z counts the number of nodes and not the number of edges. But this is just one more than the number of edges. And one gets a quadratic equation and solves this and expands this, and one sees the numbers 1, 1, 1, 3, 10, etc. So it's shifted because we count the nodes. But we can do better than that. We can actually introduce the height, and that is the longest chain of nodes from the root to a leaf, as it always is. And now we have these marked trees. And so if we say generating functions and h is a parameter, then we say the height should be less than or equal to h. So then the recursion that we had before, which was just an equation, if one introduces the h restriction, then one can say, well, we have the root, and then what happens after the root? So we have ph plus 1, and after simplification, we have blah, 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 and 1 minus ph here. And this recursion is of the continued fraction type and can be solved. I solved it by creative guessing and playing around with it, but once one has the solution, one can prove it by induction, by plugging in and simplifying. So here is the solution of this generating function, and I used an auxiliary variable v, and you see that this 1 plus 3v plus v squared that we had before when we talked about the trinomial coefficients. So people might feel that the Lagrange inversion is somewhere hidden, and it really is. And once one has this generating function and one knows what to do, one can actually compute the average height of these marked trees, meaning that all trees with the same number of nodes are equally likely. And one does this asymptotics as we learned it some time ago. And if compare this with the average height of ordered trees, which is asymptotic to square root of pi n. And here it's the factor in front is 2 divided by square root of 5, which is a little bit less than the whole thing, less than 1. So these average height is of the same order, but a bit smaller. So I don't know whether this is intuitive or not. So there are other families that are also enumerated by our sequence. And one is the unary binary trees. So you see binary trees, that would be this one, and an empty node or a root with a left and a right one. Okay, but now there's a unary binary tree, so there's also a unary edge. And in order to have this unique, we cannot allow here the empty node, because then we would have ambiguity, because then this node would occur here, but here also. And so we exclude this case here. Good. So this symbolic equation can, as usually, be translated into generating functions. And when one does this, one gets this. So this has no size. This has z, m minus 1, and z, m squared. And the quadratic can be solved. And surprise, surprise, we get again this 1, 1, 3, 10, 36 sequence. And then there are hex trees that Professor Stanley and others have considered. And they have 2 non-empty successors, or they have 3 types of unary successors, namely called left, middle, or right. And if one sets up the symbolic equation and translates into generating function, one gets the same thing. And there is no surprise here, because actually this recursive description can be sort of simplified by writing this. And this is exactly what we have seen before about the unary binary trees. So other objects of interest, multi-edge trees. They are like ordered trees, but now not edges, but multi-edges, or 5 edges, or in other cases, 3 edges. So we have to count the number of edges in this case, because otherwise you get infinitely many objects of the same size. That would not be good. So, and when I draw such objects, I don't draw 5 edges. I just write a little number 5 over the edge. And the generating function for them is given as this one. This is typical for ordered trees. You might say, well, any order k here and a root. But now it's not, and we count edges. But before it would be z, but now it has to be z over 1 minus z, because we can have 1, 2, 3, etc. edges. So if one does the simplification, one gets this quadratic. And if one solves this, well, we get the same sequence of numbers. I think truncated by 1, but otherwise the same numbers. And then the question is, of course, how can we explain this in a combinatorial way? And then another sequence that we might like is, well, you remember Motzkin paths. They have up steps, down steps, and horizontal steps. But there are also 3-colored Motzkin paths. So what does that mean? We have the horizontal steps, but we have 3 different types of horizontal steps. So as before in the hex trees, we have 3 different things. Okay, so let's call them red, green, and blue. And if one sets up the generating function for the Motzkin path, then one says, okay, empty. Or we start with 3 different types of a horizontal step, and then this quadratic factor as usual. So the difference to Motzkin is just this number 3 here, and the quadratic is this one. It's almost the same as always, except that in the beginning it's not the same, and then there's a factor z, so it's shifted. If you translate this into the coefficients, you have that multi-edge trees with n edges, but we count the multiplicities, correspond to 3 colored Moleskine paths, but length is n-1. Okay, so we have seen a couple of these guys that are counted by the same sequence of numbers. Now, let's talk a little bit about bijections. I mean, this is usually just fun. It's better, in a sense, to use advanced methods like generating functions and whatever. But occasionally, it's a lot of fun to create some bijections. So let's say we start with the multi-edge trees, and we want to build some Moleskine paths with 3 horizontal types of steps. So what we first do is we ignore the multiplicities, and then we translate this ordered tree into a Dyke path. So that's what we have done before, and this is the easiest thing of the world. Just walk around and do your thing with up and down steps. But this Dyke path can be transformed, so it has length 2n, yeah? But the Dyke path can be coded as a Moleskine path of half the length, essentially, but we have to use 2 colors to get the information back. So what we do is we erase the first and the last step of the Dyke path, and then we code them 2 by 2 according to the following rules, as you see here. So up, up becomes up, and down, down becomes down, and up, down, and down, up are basically horizontal, but we have to distinguish, and we use 2 colors for that. So I think this is very classical, although I don't know who came up with this for the first time. Okay, so far this is nothing new, but now if we talk about the multi-edge trees, so we have numbers as I promised. So here, for instance, that means actually 3 edges. And for that, we use a third color, namely blue. And the rules I'm not describing in detail, but you see that if the number is 1, then no blue color occurs. But if there is number 2, then there are some horizontal blue steps as well, according to certain rules that I'm not giving you. So all the 10 examples are here, and one can go through this. So that's a nice exercise. And there's another bijection I would want to mention briefly, namely unary binary trees and the multi-edge trees. So how do you go from one to the other? So first of all, you do the multi-edge tree and you translate it into a binary tree. That's the classical rotation correspondence. Okay, so that's one doing. And now in the next step, we have to take care of these numbers. If there are 1, you do nothing special. But if there is more than 1, then one uses these unary edges in an appropriate way. So once again, all these 10 examples are here, and it's kind of fun to discover this yourself. Okay, so then just briefly at the end, I want to mention some other things that I have seen in the Encyclopedia of Integer Sequences, namely skew Dyke path, but up, down, left in one sequence is forbidden. So for some reason, I found this in the encyclopedia, and unproven properties were given. So I thought about how can we model this. So we have our basic setting, but now we have to be careful about not seeing up, down, left. And for that, I have this magenta type of edges. So if they are not here, then we are not allowed to do up, down, left. But we can do better, and we can actually count how often we run through the magenta type edges. So this time we see four sequences, 4 layers, and recursions that one can set up. And I'm not going through the computations, but this time what happens is that the denominator that was quadratic in the previous case is actually cubic. And then using the kernel method, one has 3 factors, and 2 of them are bad, and 1 of them is good. You know that with the third order equation, you can express this solution explicitly, but this is completely useless. But fortunately, GFun helps a lot with the symbolic manipulations, and one can divide out 2 factors and express the answer in this third solution, which has the combinatorial significance. Okay, so all this can be found in a forthcoming paper that Cyril Banderier and others are editing for the Séminaire Lotharingien de Combinatoire. I thought they wanted to publish it in January, now August, and now it's September, so I'm not sure whether Cyril is online and when it will really appear. But so I collected many of these type of examples, and I think I stop here. Thank you.